The other thing, inspect your shaft. Make sure that these threads where the impeller goes in are good. If they get boogered up, that's going to be a big problem. You won't be able to get the impeller on. It'll affect your axial setting, and there'll be big problems there. If you're going to plan on reusing your shaft, and we should be able to, because our sleeve is protecting our shaft, we want to check out run out, make sure it's still straight.
This is a pretty amazing interactive class.
That's important as well. Some of the things that our millwrights use to reassemble this pump are, the oil that normally gets used is a viscosity grade 68, non-detergent isoviscosity grade 68. That's what gets used in the frame. And so when we go to reinstall the thrust bearing housing into the frame, I'd go ahead, replace the O-ring, go ahead and put your oil right on there just to make it a smooth transition. You'll also notice that at the back of the frame there is a top. It has to be orientated properly so the oil can drain back through down to the bearings. So there is a right and wrong for the way that gets installed. The other thing we like to use is a silicone loop for all the O-ring bits. So the O-rings go back on and never seize, and I'll tell you where that goes to make it easier for the next person who takes the pump apart. So once we have this, we replaced our elaborate coil seals, we can go ahead and start rebuilding this pump now. So same way it went out is going to be the same way it goes in. You got to make sure that your jack and bolts are backed off all the way. You don't want them interfering when you install it. So I'll put a little bit of iso viscosity grade 68 oil on the new O-ring. Make sure it's orientated top to top. And you can go ahead and install it in the inspected
What would be really better spin that later. We have to line up here. If we had longer studs, we could just put a stud and suck it on in there, right? We're a long stud. Go into the shop and just stuff with stud. Just back it on. You got it. There's enough clearance loosening. Okay. We were tight on the O-ring.
Put in your cap screws in the back plate.
These are real pumps these guys are working with. Real little pumps.
You need to take this in some more because your impeller's already hitting the
Through this whole process, I need you to make sure that you're constantly turning the shaft. The shaft should always turn nice and smooth. Should not have any rough spots. If you feel like you got a rough spot or a rub, that we need to take a breath and slow down because it shouldn't be like that. It should be nice and smooth through the whole process.
You guys know what you're doing?
Now,
Have you done this before?
I think so.
Yeah? Are you learning something new?
And took the back pull-out out from the field, the casing is still in the field. We're going to actually set our impeller here on the bench, which makes it a lot easier. So I need you to understand this. When you set the impeller, you're moving that whole rotating assembly axially, and that can absolutely affect your seal setting. The seal cannot be set until after the impeller
What kind of tool is that?
The impeller shaft tool.
So what does it do? It tightens it?
Yeah, tightens it.
Tightens and loosens, okay.
Now,
Found it?
our shop
Yep.
guys feel
Now we're going counterclockwise, right? I'll be towards you. All right.
We
Noise.
had it 1 year measure from the back.
You just let it drop?
Good.
Axial travel that's
Yep.
front and back of these impellers in each pump. And we know by that data.
Is this my job?
Is
that what you said?
Is this your job?
Yeah, this is
This is what you do every day?
what we do.
The front of the impeller hits the casing, the back of the impeller hits the stuffing box.
the bolts?
45,000.
Yeah, I played them in.
Gould says, depending on the temperature, they like to have it about 10 thousandths off the front of the casing. That gives the maximum efficiency of that pump, that impeller to the front of the casing. Since I know that there is 45 thousandths, our shop guys set the impeller on the bench. We're going to use a feeler gauge. We have 30 thousandths feeler gauge, and the way we're going to set that is so the back of the impeller is 30 thousandths from the stuffing box cover.
Oh well.
So right now,
This is a classic class at this event. They've had it for all 11 of their installments of this event, and this year they broke it up into 2 parts. And this is part 1 of the centrifugal pump assembly and repair class. They're going to focus a little bit on mechanical seals too in the second one, and on power.
loosen the cap screws.
Maybe we'll come around later and just trowel it, make sure it's nice and smooth.
This class
You
is
don't have
about
to
installation,
stand it all up.
startup, and commissioning of pumps.
I've seen real elaborate.
Steve's a
They're gonna make
long-time
nice
Geiger
square
employee
base,
teaching the class.
Fill it all correctly, okay, but all that makes a difference. You may even have, you may have a base where you have a riser on here, okay? And having that riser, you may have to pull the motor to get to it. You want to, because you're going to have 2 different levels of concrete, if you will, 2 different levels of ground. So you may want to do that before it in there. If you do your preliminary alignment, we do these all the time. Do preliminary alignment, pull the motor off. Well, save the shins, put them back in the same spot, put it in there, do a straight edge alignment. It's not your final alignment, but it's darn close enough to check the rotation and get some things done, okay? So we want to do a proper grouting. If you want to, you can put your initials in before it dries. Good piping practices. Oh gosh, this is one you can always go to. Always. This is talking about suction lift. All right. Not unusual to have a pump that's got a suction lift, but we got to know what we're doing with this. Okay. We got to do it correctly. We're going to get air trapped in the suction side. This self primer here, 9 times out of 10, it's a suction lift. Okay, that's what they're made for. They love it. We're going to have capacity of water in there. It'll get that air evacuated, up it goes.
An idler gear, an idler pin, and a crescent. And if you take a close look at what the thing's doing, we'll pretend this is our suction. We're pulling in fluid in our suction. It's taking a pocket of fluid around, and then 180 degrees around, you can see the gears coming back into mesh, literally pushing the fluid out the discharge. We can show that from this angle, fluid coming into the suction, around the outside diameter, and then through the discharge. The cool thing about this design pump is it works equally well in either direction. The idea is your relief valve will only relieve pressure in one direction on the back. If you rotate it in the opposite direction, you're putting pressure on the back side of the pocket, and it doesn't work as a relief valve.
Okay. Now this pump is another version of this very pump that we have here. So it's still a centrifugal pump, completely encased. You can actually, it's submersible. So you put these actually in the fluid, and then the product comes up through there's no inlet pipe. It just comes up through the bottom, goes out. So you see these a lot in municipal plants. Same, all centrifugal pumps. Every single one of them is a centrifugal pump. Okay. Now, for centrifugal pumps, there is something called the affinity laws. Has anybody kind of heard about the affinity laws? Great, awesome. So we've got some educated people in here about this. So the affinity laws, somebody has figured out at some point that there's a relationship between your ratio of flow and your horsepower, your speed, and your diameter. All those things are all related, and they're all related through the affinity laws. So, and this kind of is, I'm just telling you, we're getting a little bit into this because this kind of leads into our variable speed pump, okay? So if you have a constant impeller diameter, the ratio of your flow is directly proportional to the ratio of your speed. Okay? So we'll have an example of that too. But one thing that you'll notice, the very next one, TDH, that relationship is a squared term to your speed. And then the next one's one of the more interesting ones is that your brake horsepower has a cubed relationship to your speed. So you'll start to see your curve takes a very sharp upturn in the amount of power that's required to do different work. Constant speed pump, basically it's either constant speed or constant impeller diameter, but those are kind of interchangeable. So those same equations that we have up top and down bottom. So at the same speed, if you change your impeller diameter, it's a direct relationship to your flow. And again, the reason I'm kind of harping on this a little bit is that goes right into our variable speed pump.